Good morning and welcome to 3.8 Exponential Growth and Decay. So you've seen exponential growth and decay in previous classes. You've seen it in pre-calculus and you've seen it in college algebra a bit, and we're going to see it again, but today we get a better feel for why we use the model that we do, because we understand, we look at it from a derivative point of view. So basically, you have a worksheet that I've provided with this video, and so at the top there's some blanks to fill in. It says, when a quantity grows at a rate blank to its blank, it's growing blank. And so what goes in these what goes in the first blank is proportional. When a quantity grows at a rate proportional to its size, that's what goes in the second blank, it's growing exponentially. So whenever you read about something that is doubling at a certain rate, it's doubling its size, or it's growing at a third of the size, or it's growing at a certain percent of its size, that is exponential in nature. Or if it's decaying at a certain rate in proportion to its size, that is exponential decay. So suppose we have some function here, y. Suppose we have some function y, and it grows at a rate proportional to its size. And so I'm going to write that down. Y grows at a rate, dy dt is the rate at which y grows, and this rate is proportional. There's some constant of proportionality to its size, y. This statement right here says that the function y grows, dy dt is a rate of growth, at a rate that's proportional to its size. So k right here is known as the constant of proportionality. And hopefully you've seen direct variation or indirect variation before, where something varies directly with something. This is an example of that. This is called the constant of proportionality. We're going to name it some other things too, where y is called the size. This is the size of the y population. So this is the rate of growth. So, for instance, let me just read the statement again. It says, suppose we have some function y and it grows at a rate proportional to its size. This says that the function rate y grows at a rate proportional to its size. That's what that statement means. Okay, now let's think of it a bit from a calculus point of view. What this is saying is that the derivative of y is equal to some function, it looks like y, some constant times the function y. So think back a few classes ago, in this class, a few topics ago, when we were looking at derivatives and their graphs. Okay, so we said, hey, here's a function, what would its derivative look like? So we would say, what does the tangent line look like all along the way? And there was one function in particular that we came across whose function and derivative looked exactly alike, and it was this one. It was, if y is e to the x, y prime is e to the x. And when we looked at that from a graphing point of view, we said, oh, this is what the graph of e to the x looks like. And if we looked at the tangent lines, we said, oh, the tangent's close to 0, and then it increases, and then it keeps increasing. And it turns out that the derivative looked a lot like, exactly like the function when it's e, and a lot like the function itself when it's any exponential function. So what we know, and you can read about more details in the book, but what we can say is that when you have a function whose rate of growth is proportional to its size, you're looking at an exponential function of some sort. So that's what we can know, and we couldn't say this before we knew about calculus. So now we can talk about this. So if we look at, we could solve here for k. We could take this statement and solve here for k. And if we did, we could divide both sides by y. And we could get that k is equal to 1 over y times dy dt. Now I called it the constant of proportionality, but when we solve for k like this, k is called the relative growth rate. Now, I'm using the word growth. I could also use the word decay. When K is positive, it's a growth rate, and when K is negative, it's a decay rate. All right. So that means, in general, when we hear the words or read the words in a problem, something like grows with a constant rate of growth, grows with a constant, relative growth rate, relative, I wrote that wrong. Constant relative growth rate. When you read these words in a problem, or if it says the rate of growth is proportional to its size. When you read something to this effect, grows with a constant relative growth rate, or the rate of growth is proportional to its size. The relative growth rate is K, and K is a constant. When you read that, you're dealing with an exponential function. Or if you read that the rate of growth is proportional to its size, that's basically taking this statement, and you're dealing with an exponential function. So in previous classes, when you came across exponential functions, this is the exponential growth model, and this is the one I use. This is not the only one, and I'm going to show you how you can change it to a different form, but I like the base E, and so I would typically use, this is your exponential model. This is what I would show students, and hopefully you've seen this before. What this means is the amount after some time t has passed is equal to the initial amount times the base E raised to the growth factor, the relative growth rate, K, times T, or the relative decay rate if K is negative, times T. Now, we're going to use that. That means when you read these words, you can use this. In the first problem, I'm going to take the first example slowly to make sure we understand every little piece and why the back of the book might look different from what I've written and how you can make it look that way. And then when we do the other examples, we'll go faster. So we're ready for example 1. And so this is about E. coli. So it's kind of amazing how fast it grows. And when we do this problem, you'll see how fast it grows. So let's have a look at this first example. It reads, a common inhabitant of human intestines is the bacterium Escherichia coli. I'm not sure if I said that right. Named after the German pediatrician Theodor Escherich, who identified it in 1885. A cell of this bacterium is a nutrient broth medium, divides into 2 cells every 20 minutes. It is doubling in size every 20 minutes. So it is growing at a rate proportional to its size. This is exponential in nature. And so let's just, we understand that we're dealing with an exponential problem, okay? And it says the initial population is 50 cells. First, A, find the relative growth rate. A says, this is number 1, find the relative growth rate. Well, that means find K. That's what that means. And what we know is we are dealing with an exponential situation. Okay, so let's look at what they told us at the beginning. At the beginning, they said that the cells are doubling. There's 2 cells every 20 minutes. Every 20 minutes, it doubles. So you could either just say we don't even know how much the initial amount is, and there's 2 times that every 20 minutes, or we could go ahead and use the initial amount. Let's just do that. The initial amount, A sub 0, they said we started with 50 cells. Okay. And so what the fact that it doubles every 20 minutes means that if we were to fill this in, A of t would be 2 times 50, 100, would equal to the initial amount, 50, e to the k, and t is in 20 minutes. Now, so we would solve this exponential equation, and we could find k, and that would answer part A. So let's just do that. To solve this, you would first isolate your exponential expression. So we would divide both sides by 50, which would give us a 2. So this is e to the 20k. All right, then you would introduce a natural log, which is an inverse of an exponential, to unlock this. What about the sneeze? You can't catch coronavirus through a video, so you guys are safe, and I don't have it, but anyway. Take the natural log of both sides. The natural log of 2 is the natural log of e to the 20k. These are undoing each other, so we get the natural log of 2 is 20k. Now we'll divide both sides by 20. And so we get that k is equal to the natural log of 2 over 20. All right, so this is what k is. I went ahead and put that in my calculator, and I rounded it to a few places. So I got that k is approximately equal to 0.03466. So my exponential model would look like A, after some time has passed, is equal to the initial amount times E to my 0.03466 times T. This is how I wrote my model, but the back of the book doesn't write it that way. Let me show you what they have. What they did was, they have a different one, and this is how I made it look like theirs. I said, okay, A of T is 50 e to the, I left k like this, the natural log of 1 over 20 times the natural log of 2 times t, right? Okay, this is what it is basically. So let me show you how the back of the book made theirs look different. What they did, 1 over 20 times the natural log of 2 times t, I can rearrange these because of commutative for multiplication, so I'm going to move the t in front, times t. And since I have a natural log, you can use the log properties and kick this factor into the power of the 2. So really, you could make this look like A of t is 50 e to the natural log of 2 to the t over 20. And then e to the net log base e of something is just the something. So A of t is equal to 50 times 2 raised to the t over 20. And this is what the back of the book has for their answer. It is the same thing as this. I like the base e, and I'm going to keep base e in this. And so I could have left this number as the natural log of 2 over 20, but I like to just make it take a few decimals out, and it doesn't affect my answer. So that's why you're seeing something different in the book. It's up to you how you choose to write it, but I like E. I'm going to keep it with E. Okay, so now it says, that was part A, find K. Part B says, find an expression for the number of cells after T hours. This is part B. This is part A. What is K? What is B? Part C says, find the number of cells after 6 hours. Okay, so T is 6 hours, but I wrote my model as, I put 20, and this was in minutes. So my model's in terms of minutes. So when they say after 6 hours, first I have to say that 6 hours is, there are 60 minutes in 1 hour. What you're seeing me do here is a little bit of dimension analysis, which you've probably seen a whole lot of it in chemistry if you've ever had that. 6 times 60 is 360 minutes. I had to convert to minutes before I put it in my equation. So A of 360 is 50 e to the 0.03466 times 360. And so I get that A after 360, or A after 6 hours, is equal to, about 13,119,667 cells. Wow, that grows fast. Okay, so let me write a little statement. Now I want to, in this video, I'm going to be writing sentences on your, and I'm modeling this because I will be asking you to write sentences as well. So what can we say? Part C said, find the number of cells after 6 hours. We can say after 6 hours, there are approximately 13,119,667 cells. All right, that's the sentence I would write for part C. Let's see, what is part D? D says find the rate of growth after 6 hours. Those sound almost the same, but they are different. Rate of growth is a derivative, so that's what we have to do. So part D says find the rate of growth after 6 hours. Rate of growth when T is 6 hours. Okay. Again, I have to convert 6 hours to minutes because mine's in minutes, so 360 minutes is what I'm going to plug in. But the rate of growth means D A dt, dA dt. Now, let me just say, I used the variable A, but many times I think I used P when I did this other time because P means population. I use P of T, P sub 0. It doesn't matter as long as you know what you're doing. So dA dt is the rate of growth. So what's the derivative? Where's my function? Here's my function. What's his derivative? What is dA dt? Well, dA dt, this is an exponential function, so this is a constant, 50, e to the whatever, e to the 0.03466t is its derivative times the derivative of this. There's a little bit of chain rule, so we say this times 0.03466. So that is its derivative. What did they want to know? They wanted to know what is this when t is 6 hours, 360 minutes. So I'm going to plug that in. And so I find that dA dt after 360 minutes is equal to, I got, what did I get? I got 727. And the units on this is a rate of change, is cells per minute. Cells per minute. Okay, so if I needed to write a sentence for this, and I likely will ask you to write some sentences, we could say that the cell population is growing at a rate of, the cell population is growing at a rate of 454,727 cells per minute after 6 hours. Okay, and then let's finally do part E. When will the population reach 1 million cells? When will it reach 1 million cells? So let's do part E here. Here is my equation. When will it reach 1 million cells? What is T is what we're after. Sorry for, that's my dog playing. He's making weird noises. This is the amount. So this is 1 million. 1 million. The amount after some time has passed is equal to 50 e to the 0.03466 times t, and we're going to solve this little equation for t, and that's going to tell us how long it takes. Divide by 50, and what we get here is, what do I get? 50 goes into that. Oh, I skipped some steps here, so whatever that is, let's see. 10, that's a 2, I think 20,000 is what I get there. And then you take the natural log of both sides, and it undoes that, and then you divide this by 0.03466, and I get that T is equal to 286 minutes. And then I converted this into hours and minutes, and it turned out to be about 4 hours and 45 minutes. Now, lastly, we could write a sentence for part E and say, it will take about 4 hours and 45 minutes for the cell population to grow to 1 million cells. Okay, so I took some time on this first example and wrote sentences and went through a lot of detail because I will be asking you this sort of thing on the test. So now we're going to do some other examples. I won't take as long to go through those, but I am splitting up this video so that it's not so long of a session so you can take a little break. So I'll see you in a minute.